What happened the night before the World Cup? What?
For the World Cup. Definitely for Argentina.
Yeah.
Oh, come on, dude. Don't say
Argentina is better than Brazil.
That's messed up, dude.
Okay.
Argentina is better than Brazil.
No, Awan. Let's get started. One thing, I do have homework that I put up this more early this afternoon, like between noon and 12:30 for you. As I was going through it, I realized there was one thing. I didn't see it in the textbook when I looked through the textbook. Apparently, I just didn't look hard enough. Was talking about the energy of light. Now, you should recall we talked about the emission and absorption spectra as being spectra that are emitted or absorbed when an electron jumps from one allowed energy state to another allowed energy state. And the energy absorbed or emitted the light has to be exactly equal to the difference in those two energy states. Do you remember that? That was supposed to be a yes. Yes, we talked about that a lot. Well, I don't have a lot of space here to write, so I'm just going to go to another app, open up a blank piece of paper, and just talk about this for a little bit because, yeah, apparently we need to review it. It's coming. I want a new, where there's somewhere here that says blank or something, blank document. Okay, so what we learned was that you have specific energy levels that electrons can have in an atom. The bottom one is called the ground state. Notice that's E sub 0, but it's n equals 1. N equals 2 is the first excited, n equals 3 is the second, n equals 4, and so on. And when an electron falls from one energy state to another energy state, it gives off light with energy equal to the difference in the two allowed energy levels. Well, the thing we didn't talk about was that light has an energy according to Einstein. Actually, it was hypothesized as if this is true by Max Planck, and then it was Einstein who said, it is true that the energy of the photon is equal to a constant known as Planck's constant multiplied by the frequency of the light. So Planck's constant H is just a number 6.626. I actually am not sure of the number offhand. That's why, yeah. Phone. I'll have you look it up. Planck is how you spell Planck. I don't know. Times 10 to the minus 6 point. I think it's 626, but what is it?
It's not.
Okay. You guys wouldn't find it funny.
6.626.
Okay, good.
176 times 10 to the power 34.
Okay, it's what I wrote. Joules times seconds. Okay, so this is just Planck's constant. And so the energy of light, joules are the units we use for energy, that's J. And so the energy is just that number times the frequency. What are the units for frequency? Hertz, which is 1 per second. So if I multiply this by 1 over seconds, I'm going to get just joules or energy. And so the higher the frequency, the higher the energy of the light. Now, one of the questions that I don't think I asked was why do we worry about ultraviolet light, but we don't worry about microwaves? right? I've got my cell phone right here. And I keep this cell phone in my pocket most of the time. Sometimes I hold it up against my head. Very rarely, actually. That cell phone is constantly emitting microwaves. Why am I not worried about the microwaves? Okay, that's right. A longer wavelength, which what's the relationship between wavelength and frequency?
Shorter.
Shorter wavelength is higher frequency. Longer wavelength is shorter frequency. So microwaves have a longer wavelength or higher frequency. And because of that higher frequency, or lower, man, now I got it all backward. Microwaves have a longer wavelength, hence lower frequency. And because of that lower frequency, they have a lower energy, which we actually call the particle that contains the energy, the photon. Photon is a particle of light. So they have lower energy. We're not really worried about that. To really worry, we have to worry about energy being higher than the energy that's holding atoms together in our bodies. So if you get energies that are on the range of the energy that's holding atoms together, then the energy can break bonds. And when it breaks bonds, that's bad. That energy level required to break bonds comes in the ultraviolet range. So visible light, right? We've got lights out here. We don't worry about the energy, the radiation energy from the lights, because the energy of the photons, the particles, is lower than the energy necessary to break bonds. Ultraviolet light gets above that, then you worry. Now, all this said, we do cook food with microwaves. So is it possible that there can be danger with microwaves? Well, obviously, the microwaves can interact with material. A funny question to ask is, how does a microwave oven work? No. Well, the wavelengths or frequencies used in microwave ovens are chosen to be energies that can excite water molecules so that the radiation is absorbed by water molecules and isn't breaking them, it's making them vibrate. Or maybe it's rotate. One of the two, vibrate or rotate. And so energy is being absorbed into the water molecules. The water molecules move faster because they gained energy. But we call that higher temperature. And so the water molecules get hot because they absorb the energy, and then, of course, that heat gets transmitted through the food to cook the food. So if you have food that doesn't have much water in it, microwaves don't do a very good job because they're basically cooking water, and then the heat that's absorbed by the water can go through. Okay, so that there are potential dangers. There has been a lot of research into the microwaves used in our cell phones. And the one that I always point to as one that shows that there is at least something that people might reasonably be concerned about was they had people with telephones that they tied to their heads. And they went around with the telephone tied to their head. And some of the telephones were turned on and some were turned off. And what they found was that there was higher blood flow on the side of the head that had the telephone if the telephone was turned on, but not if it was turned off. Which means there was some effect. Now, the difference in that blood flow, just to make sure we're real clear, is smaller than the difference in the blood flow in your head when you're sitting down if you stand up. Right? So it's not like it was a major, worry. But it was just that there is, some kind of interaction going on. Generally accepted that it's not dangerous, but some people are worried we haven't stayed this long enough. We could find that by the time you guys are 60, you all have brain cancer from using your cell phones. Nobody thinks that's the case, or they would have been banned. Okay, I didn't mean to go off on a tangent, but it was a relevant thing, right? Okay, so the photon is the name of the particle of energy for light, and it has an energy proportional to frequency. So higher frequency means higher energy photons, means they can cause more damage. Back to the presentation. So that said, I'm going to start off today by talking about the solar system. So I'm going to talk about things in the solar system. What is the solar system? It's all the stuff that is bound to Sol. And what is Sol? It's our sun, right? Solar system is just talking about things that are bound to our sun. The most obvious thing in the solar system is clearly the sun, which we will learn is a massive incandescent gas, the gigantic nuclear furnace, where hydrogen is fused into helium at a temperature millions of degrees. The sun is the vast preponderance of the solar system. Notice up there I have all of the planets and asteroids and comets make up less than 1/700th of the mass of the solar system. So what makes up more than 699 out of 700 of the solar system? The sun. Right, so the sun clearly is the dominant factor here. Now, other things in the solar system are the planets. They're the biggest things that aren't called the sun. And of the mass that's not in the sun, over 70% is in Jupiter. And then almost all of the rest is in Saturn. And then you come down to the small potatoes. So we have planets. There are 4 inner planets. And you do need to know for the next test, these planets in order are Mercury, Venus, Earth, Mars. If you look at the sizes, now this shows Venus in a phase that doesn't exist there, I don't think. It's like a, 2/3 of a pi phase. I don't know why. But Venus is nearly as big as the Earth. It's like 95% the radius of the Earth. Very close to the size of the Earth. Mars is around 70% the size of the Earth. So you can see Mars is quite a bit smaller than the Earth. And then Mercury is smaller than the Moon. Mercury is a little planet. These planets here are called the terrestrial planets. They're the ones that are like the Earth. They have rocks. They are rocks. Now those terrestrial planets, the Earth is the biggest one. Which one do you suppose is hottest? Okay, somebody said Mercury. Why would you say Mercury?
Closest to the sun.
Closest to the sun. So Mercury, closest to the sun, is going to get the most radiation. And I believe Mercury is hottest on the side facing the sun. The side that's not facing the sun, though, is very cold because Mercury has no atmosphere. You need atmosphere to keep the heat in and to distribute it around the planet. Question?
And how hot is Venus compared to Mercury since it traps all of its heat in
Yes.
the atmosphere?
Venus is very, very hot. And Venus is hot everywhere because it has a thick atmosphere. And so Venus, I cannot remember the temperature. I can't. Didn't prepare for that today. But Venus is very hot. And it's hot all around because it has a thick atmosphere that traps in heat and distributes it around the planet. The Earth also has an atmosphere, which we're thankful for. We can breathe it. Our atmosphere now, we are slightly more massive than Venus. But Venus has way more atmosphere than we do. The atmosphere on Venus is something like 90 times the atmospheric pressure that we have. So if you're on Venus, you'd be getting crushed by the air pressure. Furthermore, that air would be very caustic and would kill you pretty much instantly. I mean, it would sear you, it would give you chemical burns and so on. The Russians have sent many spacecraft to explore Venus. And the longest one to survive before it was destroyed by the environment lasted something like 90 minutes. Did you find temperature?
16. Yeah, I did, and I just lost it. I gotta find it again.
So basically what we want to compare is the planet-wide temperature on Venus to the high temperature on Mercury.
What is it made of? The
What is what?
Venus's atmosphere?
You think I would know this? I think it's largely methane, but it could be largely carbon dioxide. I have to go back and check. Like I said, I didn't prepare for actually all the details of the planets today. Yes?
So it's saying that Mercury is 801 degrees Fahrenheit during the day, while Venus is about 864 degrees Fahrenheit
Okay.
all around.
Okay, so Venus is actually hotter, right? They're close, but Venus is hotter than Mercury ever gets. Farther away, so it's not just the radiation, there's something else, the greenhouse effect. Venus has a runaway greenhouse effect, we said. Because radiation gets in, how's the radiation get in? Because the frequency of visible light can go in, the infrared radiation can't get out of its atmosphere. So it traps it in. Mars. Does Mars have an atmosphere? It does, but it's like 1/100th as thick as the atmosphere on Earth. And, boy, I cannot remember its composition. Doesn't really matter because if it was 100% oxygen, that wouldn't be enough for us to breathe. So Mars has a very thin atmosphere. It's kind of funny, I've watched movies where people try to live on Mars and they build a greenhouse. In this one movie, build a greenhouse and this guy survives by living in the greenhouse, which just has flaps that he opens to walk out. Well, if it just has flaps, somehow his greenhouse increased the air pressure everywhere on the planet. Right? That doesn't make sense. Of course, it's sci-fi. So even if it's 100% oxygen, it wouldn't work for us because it's just not thick enough. Because it has such thin atmosphere, you have, once again, very wild temperature swings between daylight and nighttime. Daytime temperatures on Venus are actually not bad. You get a high temperature of around 70 degrees Fahrenheit. Yeah, remember, you'd be dead, but that's okay. It'd be a comfortable day.
Wait, I'm confused. What?
What?
Well, you'd be dead because you can't breathe. If you've got your oxygen tank on, you,
Venus?
no, on Mars.
Okay, I was like,
I have 70 degrees of what? I'm like, wait.
If you have your oxygen tank on Mars on a warm day,
yeah.
you could be out there and you'd be good wearing your shorts.
Really?
Yeah, on the day part. The night part would be a bit of a problem. Then you'd be an icicle. Because it gets really cold at night. Why? No atmosphere. Very little atmosphere. And so it doesn't keep the heat in, it doesn't transfer the heat around the planet to keep it constant temperature like Venus does.
So I have a question.
Yes.
So the gravity on Mars is different than the gravity on Earth, right?
That's correct.
So then how is, like, difference-wise, what is it like there?
Well, the surface gravity I know is less than Earth. I don't know offhand. You can do the calculation actually very simply. Like we talked about in physics class today, you just have to get the mass of Mars and the radius of Mars, and then capital G times the mass of Mars divided by the radius of Mars squared. That tells you what the surface gravity is. So these planets, we see some pretty big differences in them, but they're all the same in that they're rocks. And there is no permanent atmosphere on Mercury at all. Mercury does have gas that might stick around for a week or two, but that's it, it's gone. Can't hold on to it. Then we get to the Jovian planets. These guys are huge. And these all are gassy. What's inside that gas? What do you think? You don't have to know. What do you think?
That's what the gas is composed of, or what's in the gas itself like?
I'm going more for what's the composition like as you go in, but if you
Oh, okay.
want to contemplate about what types of gases it can be, that's interesting too.
Isn't there a
core, solid core, somewhere in the middle there?
Yes, all of them have a solid rock at the center. And in fact, as we understand things now, even the smallest of these has a rock that's bigger than Earth. So they all have big rocks. It's just that the Jovians have a lot of gas and stuff outside the rock. Now, something that's interesting is that for these two here, you will never hit a liquid-gas interface. You know, here on Earth, you have a lake. And if you jump, you know when you hit the lake because you change from gas to liquid. In those things, in Jupiter and Saturn, if you were to, quote, fall in and somehow not be dying, you would never splash. It would get thicker and thicker until at some point you say, wow, this is totally liquid. But you would never have had that splash. It just continually gets thicker until you're in a liquid state without having it change from gas to liquid.
What the?
It's one of the things we understand about how thermodynamics works. Yeah.
We talked about astronomy, and surprisingly, in prophetic guidance class. Yeah, I know. It was someone had accused of Ellen White saying that she saw red people.
Oh yes.
Yeah, you've heard of that. On what planet was it?
Well,
Jupiter. I think it was Jupiter. I think she said.
Yeah.
And then he mentioned something about it. Not like how could the people stand on there? I mean, even though it wasn't true what she said, but like, how could they stand on there if there's no? I forgot what he said. There's no like surface. So could you, if you wanted to go inside one of those planets, you could never stand on anything? But I thought you said that there's like a solid core.
There is a solid core in the center. There is a liquid-solid interface, but there's no gas-liquid interface. It just, the gas gets thicker and thicker and thicker. And if you look at a phase diagram,
oh, so just slowly gets
there
thicker.
is a maximum temperature where there's a differentiation between liquid and vapor. It's actually maximum temperature and pressure, so we call it the critical point. If you are beyond the critical point, you just can't tell the difference. Either pressure above the critical pressure or temperature above the critical temperature. Okay, so now speaking about that, right? I do want to make sure that we don't just ignore, faith issues. And Ellen White, of course, is specific to the Seventh-day Adventist faith, and this is something that is troubling. Now, Ellen White did not say Jupiter. She said, I see a planet, and she described the planet. And James Bates said, oh, now she's talking about, and he was naming the planet she was talking about. So you've got that wiggle room. She didn't say what it was. For all we know, it could have been some world way outside the solar system. But that vision was very important for the Seventh-day Adventist Church. For instance, as I understand, James Bates was the person who believed in the Seventh-day Sabbath. That wasn't Ellen White. So he's the one who brought the seventh-day part to Seventh-day Adventists. And he was convinced that Ellen White was a true prophet because what she was describing about the planets matched the best known astronomy of the day, which does not match the astronomy that we know today. And so, like I think the White Estate says that the purpose of the vision was not to relate the truth, it was to convince James White that she was seeing real visions, which is kind of mealy-mouthed because then you're like, how do you know she didn't prep for this? And study what the present knowledge was and then give it to him. Right, so it's troubling to me, but what can you do? You have facts and you have to try to make sense of them.
Yeah, but it's true. If she would have said like the knowledge we know today, he wouldn't have believed
He would say,
her.
you're full of it. Everybody knows that's not what it's like. It says. Yeah. Okay, so getting back to this, the outer planets, you do need to know again the order: Jupiter, Saturn, Uranus, Neptune. All of them have lots of atmosphere, have a rock in the center. All of them have lots of moons. How many moons does the Earth have? Uno, eins, ich. Any other languages we can go to? We have one. Now, some people say, oh, we have another one. We have another quasi-moon. Do you know we have another quasi-moon? It's quasi because it's not permanent. It's in an orbit that has it looping with us for, I forgot how long, but eventually it's going to take off again. And it's really tiny. And then we have all the man-made satellites. Call those moons if you like. So the Earth basically has one. Luna, or whatever you want to call it. Mars has two. Phobos and Deimos. Or fear and terror. They are like twin children of... Oh, I forgot that. So Mars has two. Mercury has 0. So we got 0, 1, 2. How many does Jupiter have? Lots and lots. But how many did Galileo find?
4.
4. And so there were people who posited, I see a sequence, 0, 1, double 1, you get, oops, 0, 0. Venus also is 0. 1, double 1, you get, okay, 1, double 1, you get 2. Double 2, you get 4. They said, hey, double 4, there should be 8 somewhere there for Saturn. Turns out that's not true at all. Saturn, if you're going to try to count the moons of Saturn, you'd have a problem. Because its ring is really a whole bunch of ice balls. Some of them size of houses, some of them, size of sand. So are you going to count those or not? I don't know. Gap in the rings. The gaps in the rings are caused by other moons. You have two phenomena. You have shepherd moons and you have resonances. But you have one major moon for Saturn and then a bunch of small ones. 4 major moons for Jupiter. Get out to Neptune, and Neptune has 1 major moon. And Uranus doesn't, I don't think it has any really major moons. Obviously, they all have moons. These out here have lots of smaller moons. I don't think there's anything else to talk about with the moons. Let's go on to the last couple things on here. Asteroids. Asteroids are little rocks. And I say little. There is one exception. The vast preponderance of the mass in the asteroid belt is in one asteroid, Ceres. Ceres is, I think it's like 80% of all of the asteroid mass is in Ceres. Now, when you watch Star Wars, what do you tend to think of for asteroids? You have an asteroid field, and what does, I don't know, Luke or whoever's piloting have to do when he's going through the asteroid field? Yeah, it makes Star Tours a great ride, right? But the reality is that when you're going through an asteroid field, it's mostly empty space. There are few and far between. But, it doesn't work as well for sci-fi. The asteroids are little rockets out there. The asteroids are not exclusively in the asteroid belt. The asteroid belt is between Jupiter and Mars. But there are some asteroids that we call Trojan asteroids. You guys know the story of the Trojan horse. Say goodbye to my wife. Thank you. You guys know the story of the Trojan horse, right? Yeah. Yeah.
Troy.
Yeah. Yeah. The people from Troy, right? Trojans.
Okay.
The Trojan asteroids are following that idea. They're asteroids that are hiding out near Jupiter. So Jupiter has asteroids that travel with it as it orbits. So they're called the Trojan asteroids. They're hiding with Jupiter. And there are other asteroids that are not just between Jupiter and Mars. Go out further and you get to Pluto. Right now, Pluto is farther than Neptune. Sometimes Pluto is closer than Neptune. Usually it's farther. Pluto used to be called a planet. called a planet because it was predicted to be a planet, but it turned out it just didn't have the properties. I saw an article just a week or two ago saying scientists believe they were wrong in declassifying Pluto as a planet. I don't know who wrote it, but it was, no, they don't. The person looked at basically the definition of minor planet. Pluto is now a minor planet. They made up a new category for Pluto because they didn't want to just completely cut it loose and just say you're a Kuiper Belt object like the other objects out there. So they made up a new object that is a minor planet. And so Pluto's a minor planet, or it says here dwarf planet. That's a technical term. And dwarf planets are things that have enough mass for gravity to pull them into a spherical shape, but they don't have enough mass to be the dominant object in its orbit. So, and they have a mathematical way of calculating these things that makes a clear distinction that Pluto doesn't fit in the others do. Now, why do people want to demote Pluto in the first place? It's fundamentally not like the others. Planets it comes from a Greek word that means wanderer. When I'm teaching, I'm like a planet, I'm up here wandering, right? The planets were the wanderers because remember we have the celestial sphere here, and all of the stars appear fixed on the sphere. You know this is just a model, but they appear fixed on it. Whereas the planets appear to wander across the celestial sphere. And so that's why they were planets, because they could see them wandering. And so what were the planets? Well, they saw Mercury, Venus. Earth didn't count. Earth was us. Mars, Jupiter, Saturn. Over time, with improved optics and telescopes, we have the discovery of Uranus. Uranus was discovered by William Herschel and his sister Caroline. Actually, somebody else had discovered it first, but didn't know what it was and just kind of forgot about it. So it was discovered, and then as astronomers were, by the way, William Herschel was really interesting. He was like the royal astronomer and musician or something like that. And if it was cloudy and the king wants to see the stars, why, the king will see stars. And so he set up his telescope in the backyard, and he would put little lanterns with little cutouts and would just aim the telescope at the little lantern so the king could still see stars even if it was cloudy out. Honesty is, it's not worth losing your head over, is it? Anyway, so as scientists start studying the orbit of Uranus, who I believe Herschel wanted to call George's star for King George, but that was not allowed because the planets must have godly names, and so it was named Uranus, which is okay. You can pronounce it Uranus or Uranus.
Yeah.
Neither one is perfectly free from any jokes. I say Uranus because it's free from the worst of the jokes.
Yeah, true.
So, as they studied the orbit of Uranus, they discovered that it really wasn't doing the right things. We've learned about Kepler's laws and then about Newton and his law of universal gravitation. And that predicts very accurately what the motions of the planets should be, but it failed to predict very accurately Uranus. Uranus had some little wiggles. And so the scientists said, well, what would cause these little wiggles? There must be another massive object that's orbiting the sun, and they calculated what its radius would have to be and what its period would have to be. And they said, right now it should be right here. So they look up there at the telescopes, and they found it. And so the first predicted planet was Neptune. And everybody cheers. And then they start studying the orbit of Neptune, and they discovered that Neptune just doesn't behave right. And so they went through the same process, and they predicted there should be another planet here. You look up there at the telescopes, and they found Pluto. That's how Pluto became a planet. But very quickly they realized Pluto doesn't have the mass necessary to cause these wiggles. So they realized quickly, we were wrong. Pluto is not what we were looking for. It was not the droid they were looking for. But it was accepted as a planet because it was found. Just for the record, you look at the periodic table, Neptunium is the first man-made element. You look on the bottom row, you have uranium. The first one beyond that is Neptunium, NP. Plutonium, the second man-made element, using the same naming schemes for the two. Obviously, they discovered by prediction the planets before they created the elements in the lab. Coming back to this then, that's why Pluto was first a planet, why it's not now. There are very simple things about Pluto that make it not fit in. Not a wanderer that you can see with the naked eye. Uranus and Neptune are also not wanderers we can see with the naked eye. They wander, we can't see with the naked eye because they're too far away and too small. Right? They just don't reflect enough sunlight. If they were huge, now they are very huge compared to Earth, right? You can tell by looking at the picture. But if they were huge, yeah, we could see them. If they were closer, we would see them. But we can't see with the naked eye, we can see with the telescope. And scientists concluded, okay, look, it's got all the properties. It's just so far away. Hey, it's not Neptune's fault. It's too far away. And so it's a planet. But Pluto is like half ice, half rock. Doesn't have a big rock at its core. It's small. It has a moon. It has a moon. Charon, the boatman that takes you over the river Styx, that is like 1/3 its mass. And that's a big moon compared to the object. Now some people say, oh, but it has a moon. Shouldn't that be planet-like behavior? Well, there are plenty of asteroids that have moons, like Ida and Dactyl. Right? They're pretty small asteroids, but you still have like this. If you were to believe in the Weekly World News, there was a boy born so fat that he had asteroids going around him. And that story was so successful, they came back with life had spontaneously started on the asteroids orbiting that baby boy. But I don't believe that to be true. Call me a skeptic. I don't believe in flat Earth. I don't believe there's a boy so fat. Okay, let's not be ridiculous. Let's just go on. So, going out further than Neptune, we have this thing called the Kuiper Belt. Now we're getting to things that, when I started teaching astronomy, which is around 22 years ago or something like that, the Kuiper Belt was like, well, we're pretty sure it's there. We've got a few objects out there that we found. It was predicted by an American astronomer, so we do know we should pronounce the name Kuiper. Because if we were to use the Dutch pronunciation, which was his heritage, it would be the Kuiper Belt. So, the Kuiper Belt. The Kuiper Belt is a bunch of icy objects out beyond Neptune. What's an icy object out beyond Neptune? Pluto. Pluto is a Kuiper Belt object. It's an object that's out there. Now, there's a lot of different names that fit Pluto. It's, let's see, I think it's a Cubano. There's a couple different names. Trans-Neptunian object, because it's something that has a semi-major axis bigger than Neptune's. So the Kuiper Belt are objects that are orbiting beyond Neptune that are largely icy objects. And right now we know of a lot of them, and some of them are big objects. In fact, Pluto is not the biggest Kuiper Belt object. The biggest Kuiper Belt object is believed to be, that we know of, is believed to be Eris. You see I have there, including Eris, more massive than Pluto. Now, something interesting in 2015, the New Horizons spacecraft flew by Pluto and took very detailed images and measurements of Pluto that we just didn't have before. And we learned lots of things about Pluto that we didn't know, including that Pluto's size was not quite what we thought it was, because we weren't sure how thick the atmosphere was. And so with that discovery, Pluto's size turned out to be a little bigger than we thought it was, making it closer to Eris in size. These other objects out there that are in the region of Pluto, in the Kuiper Belt, that are of similar size include Makemake, Haumea, and Quaoar. Quaoar was the first big one to make people really question if Pluto was special. Quaoar, at least as of last check, I did not check before lecture today, I should again, if Quaoar has been elevated to a dwarf planet. Most people believe it should. Also, I think it's important to point out, there is one person who is responsible for our understanding of everything in this list that's not named Pluto here. His name is, I think, Mark Brown, but he is the one who's finding all of these, him and his research team, finding all of these objects that are similar to Pluto. I came over here, I don't know why. I'm going to move on. Here's a picture of Pluto. Before 2 years ago, all we had for Pluto was a fuzzy blob. And now we have these high detail pictures. You might have seen pictures that kind of looks like Snoopy on there, or some people think it looks like a heart because, it's neither, it's just a formation. But you look here, now we have a lot of interesting information that has been discovered about Pluto. So it's good to go. The New Horizons spacecraft will be going to visit another object out there in the Kuiper Belt to try to learn more about other objects that are out there. Just some history about Pluto, some things I've already said. It was 1930 when it was discovered and classified as a planet. I can't believe I left that second line there. Was only the largest of thousands of bodies orbiting the sun in the Kuiper Belt. Well, it's not the largest, right? Second largest that we know of. Coming down here. This one's an important one to note. There are 7 moons in the solar system that are larger than Pluto. Yeah.
So, you said people thought Pluto was a planet because it was pulling Neptune, right?
They thought it was pulling Neptune, but they quickly realized it didn't have enough mass to pull.
So, what causes the irregularities in Neptune?
That's a really good question. And the answer is, we didn't understand physics good enough. The answer is, I like to be nerdy, okay? You'll learn that soon enough. With Einstein's theory of general relativity, we understand that a massive object warps the space-time continuum around it. And what that means is lengths are different when you're around a massive object and when you're not around it. Time travels at a different rate when you're close to a massive object compared to when you're not close to it. And the odd behavior of Neptune, of Uranus, turns out to be perfectly explained by the theory of general relativity and a better understanding of gravitation. And so there was no need for the additional planet.
Wait, so you're saying that the time would go slower in Uranus?
It passes at a different rate. And so
an hour in Earth is different as an hour in Uranus.
if you had 2 watches that keep perfect time, and you're on the surface of the Earth so you're in the same place, they keep exactly the same time. You take one to the surface of Earth and one to the, quote, surface of Uranus, and then you come back together, the clocks won't be the same anymore. And that's, you might have seen in the movie, what was the movie? Is it Interstellar?
Yeah.
The one where you have the scientist who's been working down on this planet, and
Those of his children are.
he did not age very much.
Yeah.
So when you're close to a massive object, time just passes at a slower rate. And that's a true effect.
Wait, so if someone were to be like an astronaut out there, whatever time is it's different when
Yes.
you're. Oh my gosh, I'm sorry. Okay, sorry, that's just my way.
Okay, so in 2006, which has been a long time ago now, that's when astronomers demoted Pluto. So pretty soon I'll have people who didn't grow with Pluto as a planet, and then I would have to have people who are all, but I like Pluto. And they decided that a planet must meet two definitions. It must have enough gravity to pull itself into spherical shape, and it must dominate its neighborhood, clear it out any large objects. And the second part is what keeps Pluto from being a planet. So going beyond the Kuiper Belt. The Kuiper Belt is not the end of the solar system. You go beyond the Kuiper Belt and you have the Oort cloud. And the Oort cloud is different than the Kuiper Belt. Everything I've talked about up to the Oort cloud is all pretty much in a disk. All flat. Everything orbiting around the same circle. So the Kuiper Belt is in the same disk, just farther out. But the Oort cloud is spherically symmetric. You have stuff in all different directions. And when I started teaching astronomy, nobody knew of any Oort cloud object. It was only a theory. Now there are a lot of known Oort cloud objects. Notice it says located around 50,000 astronomical degrees from the sun. What does that mean?
It's 50 times of this.
50,000 times farther away than the Earth is from the sun. So it's way out there. And occasionally, a passing star will cause one of these objects out there in the Oort cloud to have its orbit deviated a little bit. And if it's deviated a little bit from doing a nice circle, it's going to become more eccentric, which means it's going to come plunging toward the sun. And when this ice ball comes plunging toward the sun, as it gets close to the sun causes it to sublime, that is, go from ice into gas. And then it gives off a lot of gas, and we see sunlight reflected from the gas, and whew, we have a comet. And so as it comes around the sun, you have a comet for a while. It goes back out there. Remember, it's going to go really fast when it's close to the sun, really slow when it's far away. So these comets may be out here for a couple hundred years, and then for a couple months we have a comet, and then it goes back out there for a couple hundred years again. So the Oort cloud is responsible for comets that have long periods. That is, they don't return but every couple hundred years. The Kuiper Belt is responsible for comets that have the shorter periods, ones that might come by every 10 years. Well, longer than 10 years probably, but and the ones that come with short periods are all in the plane. That's why Kuiper predicted his Kuiper Belt. The ones that are longer periods come from all directions. That's why Oort predicted his Oort cloud. So they're the same type of objects. They're ice balls, but they're some closer and in the plane, some farther away, and all around. Here's a picture of a comet. It's kind of cool, right? Here you see the actual ice of the comet, and when it gets close enough to the sun, you have a lot of gas coming out. You can see there's gas coming out, and we'll talk about comets later. The comets are ice balls that have come close enough to the sun. Yeah, I'm out of time, really. Everything in the solar system generally is in the same plane and rotating in the same direction, but there are some anomalies. Anomaly number one is Venus. Venus rotates backward. So remember, the Earth, we're rotating like this as we go around. Venus is doing like this, but really slowly. It's rotating backwards. Notice that I'm orbiting this direction, but I'm rotating the opposite. That's what Venus does. How can Venus rotate the wrong direction? Everything else, well, except for Uranus, rotates the same direction we do. Rotates the same direction it orbits. Why? How could Venus do it backward? That would be the kind of interesting thing you would observe in the scientific method, right? And so what would your next step be? It would be come up with a hypothesis, me asking why. Lots of ideas have been explored. We don't know for sure what the answer is. Some people say maybe there's no real reason it should go that way. But the general consensus is it must have been like the rest of us, rotating the same direction it's orbiting, and then something struck it, and it struck it off axis and made it start going the opposite direction. That would be a pretty big rattling strike. You get down there to Uranus. Uranus, you see, is on its side. So Uranus, its pole will sometimes be pointing at the sun almost, which is really crazy. It would have the most extreme weather variations because of that extreme, see, 97.9 degrees. That means it's considered backward as well. But 90 would have been straight on like this. Okay, we're out of time. I'll see you guys for lab tomorrow, yeah? Yes.